Welcome back everybody to another second year physical chemistry lecture, and today we are going to deal with equilibrium reactions. What will be covered and why? Thus far we have discussed mixtures and their chemical potentials. But what happens if mixtures start reacting and set up an equilibrium reaction? Thus today we will discuss equilibrium constants. What you will need. Atkins' physical chemistry. It will be a new section called chemical equilibrium, the equilibrium constant. And naturally, you need to remind yourself of the previous lectures on chemical potential. And as for mathematics, you'll need calculus, differentiation. Today is quite an involved lecture, but it's an important one. Extent of reaction. So now imagine a simple acid dissociation reaction for acetic acid, which we can see here. You have COOH, that's a carboxylic group, and it sets up an equilibrium with the deprotonated acetic acid, denoted COO minus plus H+. We can't discuss the idea of a reaction going to completion in a reaction as the one above, since not all reactants is consumed. For example, the number of moles of reactant does not reach zero when we reach equilibrium. So instead, we have to discuss a slightly different idea, the idea of an extent of reaction. In other words, how far along it goes before it stops. So for example, in the above case, when we lose 1 mole of COOH, we gain 2 moles of product. Hence, our extent must also include stoichiometry. And so our extent must be able to quantify both products and reactants such that when we reach equilibrium, the change in extent is 0 for everything. So if we were to inspect only one species and not all of them, and we're able to follow its extent, when it reaches 0, or we know all the other species also have reached 0 extent. So this is all very abstract, but let's get a little bit more concrete now. Extent of reaction is denoted with the Greek letter chi. It looks like a fancy E. And what it does, it will take into account moles and stoichiometry. And we define it as follows. That the change, the infinitesimal change in the number of moles, dNi, or species I, is equal to the stoichiometric value of I in the reaction, nu I, nu looks like a V, times the change in the extent of the reaction. Alright, now we're going to get back to one of our favorite equations, which is the Gibbs free energy equation as a differential. And we are going to do is write down its form when we're under constant pressure and temperature conditions. That means dG is equal to the sum of all chemical potentials times the change in the molar quantities. We should now be very familiar with this equation, and that this equation gives us a lot of information about all sorts of chemical systems. And let me just remind you that this equation says that the change in the Gibbs free energy is equal to the change in the chemical energy of the system. Alright, with this in mind, let's substitute in the definition for our extent of reaction. And it's very simple. All we do is replace that dNi with a new I, d chi. Since d chi is global, as in that it is the same value for all chemical species, we're able to bring it outside the brackets. So remember when I said that we want whatever this extent parameter is, all we have to do is be able to inspect one species and see that it's come to equilibrium, and then we know that all the other species are in equilibrium. So that whatever the parameter must be, it must be common to all species. And as you can see here on the second last line of the slide, d chi achieves that. We're able to separate it out from all chemical species. It's common to all of them. That's wonderful. That's what we want. All right. We then take the next step, which is we just recognize that what we have is a derivative equation. But the derivative is the Gibbs free energy with respect to d chi, which we write here at the very bottom on the left-hand side. And you'll note I denote it with P, T to say this equation is only true if we've got constant pressure and temperature conditions. We know this, of course, because that's where we started at the very top of the slide. And you'll note that this derivative is equal to the sum of all chemical species multiplied by their stoichiometry. All right, now this is our master equation, which we've just derived. But as you can see, there is a price we pay for writing this equation in terms of chi. We are stuck with what is essentially a partial derivative. All right. What we are now going to have to do is define a new kind of Gibbs free energy function, which we denote as delta subscript r g is equal to this dg d chi parameter. And this is called the reaction Gibbs energy. So I'm going to say that again. This is called the reaction Gibbs energy. Now, before we keep going, I want to point something out which is immensely important. This reaction Gibbs energy is still an energy. In spite of it being a derivative, when you look at its units, you will find that it is just joules. Chi is dimensionless. All the mole information, the molar information from previous, well, it's all locked in the stoichiometry parameter or nu I. So when we say this is the reaction Gibbs energy, we are absolutely correct in calling it an energy, because that is what the unit analysis will give us. But it's important to remember that technically it is a derivative. All right. The reaction Gibbs energy is defined as the slope of the graph below. All right, this graph you can go and find in Atkinson's physical chemistry. And I think this is very useful visually to see what happens. The extent of reaction chi. You can have zero extent from the one end, and then you can say completion on the other, which is where you would have products. But the extent of reaction, when you take a look at the derivative with respect to the Gibbs energy, will equal zero at equilibrium, which you can see here. If you start off pure reactants, your slope will be negative. Because your reactance is not at equilibrium yet. And you will go down this slope to the very bottom of, say, which in this case looks like a parabola, and you'll find the minimum point, which is when the derivative equals zero. Because the gradient of this slope at this point is zero, and that's your equilibrium point. If you go to the other side, where you've got more products, your derivative, or your delta Rg will be greater than 0. How do we know that? Look at the curve. It's got a positive slope. Therefore, the derivative or gradient must be positive. The big takeaway is at equilibrium, delta Rg is equal to 0. And why? Because we want to minimize the free energy. Alright, so the reaction Gibbs energy. We'll now do an example. We will go back to our acetic acid equilibrium from before. We'll write out delta Rg is equal to the sum of mu I, nu I. And you'll note that all I've done is I explicitly wrote out the sum for each chemical species, including the carboxylic acid group, both protonated and deprotonated, as well as the H+. Now, if you go and look at that reaction from before, you will note that the stoichiometry is very simple. For COOH, that new parameter is equal to -1. Basically, it says for every that we lose a COOH, and that leads to that we gain a COO minus and a H+. Hence, the stoichiometric parameters for the deprotonated species in H+ is +1. Now, at equilibrium, we know that delta Rg equals 0. Hence, we can rearrange our equation as follows. That 1 times mu COOH is equal to 1 mu COO minus plus 1 mu H+. And so we come to a very important conclusion, which is at equilibrium, we can say that the chemical potentials of the products, that's the species on the right, and the reactants, that's the species on the left, are in balance. Alright, let's use our example and substitute in for the chemical potentials. Now, by now, we should all know what the chemical potential equations look like in general form. The substitution we are going to do is we're going to do the most general we can, which is to make sure that we include activities, because that accounts for all real parts of the behavior of our species. So, it's very simple. We do that substitution. You get quite a long equation, but you'll note in our chemical potentials we have to have our standard state plus the RT log activity component. Then we have to rearrange things and clean things up. And what I've done is I have put together all of the standard state components plus all the activity components. And what you can then do is you can redefine all those standard state components as an overall standard state Gibbs reaction energy plus RT log activity of the products on the top times the activities of the products at the bottom. Now this brings us to reaction quotient and constants. You should hopefully now start to see the origin of the equilibrium constant coming out. From before, we have our Gibbs reaction Gibbs energy, which I've just reproduced here. And what we're going to do is we're going to say that part of the equation that deals with the activities we'll redefine as Q, which is the reaction quotient. Again, note, products on the top, reactants on the bottom. And at equilibrium, we know that delta Rg equals 0, and hence we can say that delta Rg standard is equal to minus RT log K, where K is the equilibrium constant. And that, I hope you can see, is where the equilibrium constant comes from. It comes from the chemical potentials of all the species in your reaction. It's just a quantification of chemical potential. That's what it is. And Q also quantifies that, but it quantifies it when you're not at equilibrium. Alright, now what we had before were examples, and an example I should say, which is for acetic acid, but you can make this equation general for any reaction you choose to inspect. Delta Rg equals delta Rg standard plus RT log Q, where Q is equal to this funny function. That letter that you see there is capital pi. That's pi as in the letter pi in the Greek alphabet. Capital Pi I, AI to the power of the stoichiometric parameter. And at equilibrium, that Q becomes a K. You might find, well, that's a bit intimidating. What is this capital Pi thing? You've never seen it before? Well, its idea is very similar to that of the sum sigma, which you've now been introduced to. However, in sigma, or the sum, where you add things, the capital Pi is for when you multiply things together. So here's a very basic example. Capital Pi I, x of I can be whatever variable you want to choose. And that's just equal to x1 times x2 times x3 times etc. Now, I remember these things in my own mind, and hopefully this would be useful to you. I like to remember these differences as follow. S is for sum, is for sigma. P is for product. In other words, multiplying, is for pi. Hope that helps. Alright, now the key concepts I want you to take away. Equilibrium reactions need to be treated with care via the extent of reaction, where we define the reaction Gibbs energy, delta Rg, as equal to the derivative of dG with dchi. And remember, that's at constant pressure and temperature. An equilibrium reaction is described by the following reaction, which is delta Rg is equal to the standard state energy plus RT log Q. And Q is basically the product of all activities to the power of the stoichiometric parameter. And at equilibrium, when delta Rg equals 0, Q equals K. Alright, that's the end of the lecture. We now have the quiz, and there are 2 questions which are multiple choice. I'll read it out for you. Question 1. You measure the reaction Gibbs free energy and it is 5 kilojoules. Is the reaction A, still going? B, at equilibrium? Question number 2. From question number 1, do we have an excess of products, an excess of reactants, or equilibrium between chemical potentials of products and reactants?